All right, the first part of this review is graphing transformations. And remember, we're going to do all of the nice points that fit on our grid from our original parent function points. So for the first one, I gave you one of these special case problems. We have a y-axis reflection and a horizontal shift. We have to factor the negative out to see which way we're actually shifting. So this is a y-axis reflection. You can also think of it as negative xy. And then all of the points are actually going to the right 5 units instead of to the left like it looks like originally. So I'm not going to write out all of the points for these. I'm just going to move the square root function, which should be at 0, 0. I'm going to move it to the right 5 units. And I know that the original parent function looks like this. So a y-axis reflection should be opening to the left. There's no other stretches happening, so I know that from the vertex it's over 1, up 1, over 4, up 2, over 9, up 3, and I may be able to fit over 16, up 4, but I'm just going to stop there. Those are our parent function points, so that's good enough. Okay, and then, sorry, that's going to bother me. And then, don't miss that one this time. For the next one, we have a cubic. And this is a y or an x-axis reflection, so every y value will get changed opposite sign. And then we're going left 2, up 1. So again, depending on how well you have your parent function shapes memorized, you may or may not need to write out all of the points. So I remember that this parent function normally has kind of a center at 0, 0. So I'm going left 2 and up 1. And normally the cubic graph looks like this. So when I do an x-axis reflection, it's going to go this way. So from the center, I know that it's going to go left 1, up 1, right 1, down 1. Also from the center, left 2, up 8, and right 2, down 8. And that's all that we normally sketch in. I usually only take the time to write out points if I have a stretch or a dilation. Technically, there is a vertical dilation for h of x here, but this is an absolute value function. So remember, you should just be thinking about slope being plus or minus 3/4, and the fact that this absolute value function should open up because this is positive. This graph has been shifted to the right 3 units and down 2 units. And then from that vertex, I'm going up 3 and right 4 in one direction, and then from the vertex, up 3 and left 4 in the other direction. And I'm only requiring that you get 3 points for an absolute value graph, which again we put on our notes on the parent functions page. Now we didn't have cube root functions in the parent functions, so but we have had this in our homework. This is also a special case problem. Again, anytime you have a number in front of x and a horizontal shift, you need to factor whatever's in front of x out. Now, every x value will get divided by 2. And then after that, we're shifting to the right, but only 2 units instead of 4, like it looks like originally. So for this one, maybe I will write out some of the points. So the original point, I don't have room to write the originals and the new. Well, yeah, I guess I do. Let me start here. Originals, xy. We have -8, -2. Cube root of -1 is -1. 0, 0, 1, 1. Cube root of 8 is 2. So if I do this math to those, then I cut all of the x values in half. I get -4, -2, -1/2, -1, 0, 0, +1/2, +1, and +4, +2. So these are the transformed points, and then I need to take all of these and go to the right 2 units. So I'm just hovering my pencil over -4, -2, and then I'm going to move to the right 2. negative 1/2, negative 1, and then go right 1, 2. 0, 0, go right 2. Positive 1/2, positive 1, then right 2. And you should see some symmetry happening around where the center is. And then 4, 2, and right 2. The cube root graph, we're going to talk about inverses in chapter 1, section 6, but it's the inverse of the cubic graph. So it has the same shape. It just kind of looks like it's been rotated in some way. So we'll talk about that. All right, number 5 is an x-squared graph. It's been reflected across the x-axis. We have a horizontal dilation of 1/2. A horizontal dilation of 2 because there's a 1/2 here. So what am I talking about? Every x value gets divided by 1/2, and every y value gets the opposite sign that it had. And then after we do that, we'll go up 7. Okay, so if we write out these original points, we've got 0, 0, plus or minus 1, 1, plus or minus 2, 4. These are the originals. Plus or minus 3, 9. Okay, so what do these become if we perform this math? So then we get, if we're dividing by 1/2, you're really doubling everything. 0, 0 stays the same. And then we get plus or minus 2, negative 1. Plus or minus 4, negative 4. And plus or minus 6, negative 9. And then all of those are going to go up 7. So I'm going to start at 0, 0, and I'm going to go up 7. And then I'm just going to start at 2, 1 was one of the points. 2, negative 1 was one of the points, and then I go up 7. And then you can kind of use symmetry so that you're not hovering over a bunch of points, losing track. Okay, and then 4, negative 4 was a point, and then I can go up 7. And again, use symmetry, so 4 units across, 4 more units puts me there. So see how you're getting that symmetric shape. And finally 6, negative 9. And then we go up 7, so that would bring us here. And then we can reflect that over here. And I'd say that's a pretty good parabola there. Someone asked me on Friday, I think it was, is a horizontal stretch the same as a vertical shrink? And the answer is no. They both make the graph look wider, but they don't change the shape at the same scale or rate. So that is different. This is different than me just saying 1/2 y. Okay, and then I have an absolute value. I put another absolute value on here because, again, we don't really treat this the same way we treat the others. This is still, even though this is on the inside, this is still a slope. And I'm still saying this absolute value opens up, and it's got a slope of plus or minus 1/3 on either side. This vertex has been shifted down 4. And then I do a slope of 1/3 from the vertex, positive and negative, going in either direction. And that's it. Okay, so what about these dilation factors? These can get kind of confusing. So I tried to have this, remember, this is your vertical dilation, and whatever the factor is, it will be the number that you put in front of the equation. It's horizontal, that is always kind of weird. So horizontal dilation, whatever number we put into the function notation, the horizontal dilation was by a factor of 1 over c. So whatever factor they give us, we flip that to put it into the equation. All right, so vertical dilation by a factor of 3. So let's see, transformation of f of x to g of x. So this is going to be g of x equals 3 f of horizontal dilation by a factor of 4. So that means that 1 over c is equal to 4. In other words, c is equal to 1/4. If you flip this and flip this. So what does that mean? We put 1/4 x, or we put x over 4, however you want to look at that. Okay, horizontal dilation by a factor of 1/2. So that means that c equals 2. So far I've got g of x equals something f of 2x, right? So when the horizontal dilation is a fraction, we have a whole number in here. When it's a whole number, we get a fraction in there. Okay, and a vertical dilation by a factor of 3. Vertical dilation takes no thought, just put that number out in front. And x-axis reflection, then a horizontal shift to the right 3, then up 5. Right, so we have an x-axis reflection, which is out in front, right? So we have g of x equals negative f of, shift this right 3, x minus 3, and then go up 5. If we do the shifting first, we had this in a homework somewhere along the line in one of our bookwork assignments. Shift down 10. So here's what we have so far. Shift down 10. And then do both an x-axis and y-axis reflection. Okay, so that means that the y-axis reflection is the easy one. Plug the negative in for the x. But the x-axis reflection is not just putting a negative out in front here like this. You're multiplying the entire function by a negative. So because the vertical shift down 10 was supposed to be done first, when we simplify that equation, it really looks like this, negative f of negative x plus 10. So if you were just looking at this equation, you might say go reflect and then go up 10. But that's the same as shifting something down. And then once you shift something down here, if you reflect it across the y-axis and across the x-axis, it lands up here. So that's why that's kind of strange. Okay. Tables. This can get confusing, right? So we need to practice working with tables. They'll be all over our AP test. We use them all year. We're using this for questions 11 through 18. So fill in the missing values of the table given that f of x is an odd function and g of x is an even function. Odd function, you need to know this definition. F of negative x equals negative f of x. What does that mean? I'm trying to figure out f of negative 1. It equals negative f of 1. So if f of 1 is 2, it equals f of negative 1 equals negative 2. If f of 2 equals 2, f of negative 2 equals negative 2. G of x is an even function. You need to know this definition as well. So this definition means that g of negative x equals g of x. That means that if g of negative 2 is equal to 0, then g of 2 is equal to 0. If g of negative 1 is equal to 1, then g of 1 is also equal to 1. Remember, odd function is your origin symmetry. So if you were to plot these points for f, we should see them in diagonal quadrants. And even function is y-axis symmetry. So if we were to plot those points, we should see them at the same height on either side of the y-axis. Now that we have our table filled in, let's evaluate f of 1, and then g of negative 2 and g of 2. This is just making sure you know the basics of a table. So again, we did this in our packet a lot, but it's easy to get things mixed up. So this says when these x values are all inputs, and the values that were given for f and g, these are outputs of the functions. So when the input is 1, what is the output for f? 2. When the input for g is negative 2, what is the output for g? 0. When the input for g is 2, what is the output for g? 0. All right, so input, output. And now we're going backwards. Find x, find the input when the output, when the y value, is equal to negative 2 for f. So I'm looking at f of x. F of x is negative 2 in 2 spots, here and here. So there are 2 values for x. X equals negative 2 and x equals -1 are both solutions that make f of x equal to -2. And when is g of x equal to 4? So find the input that makes that happen. So here's 4. The input is 0. All right, and then let's do some of these compositions. We had this all over our packet over the weekend. So remember, you start on the inside, and it's a good idea to write these down. I know some of you can just kind of like hop around the table, but it's also like if you're just hopping around the table, um, if you need to go back and look at what you did, that's kind of hard to do because you don't have anything written down. So it's not a big deal to write this stuff down. If I say g of 1, when the input is 1, what is the output? 1. Now it's f of 1. When the input is 1, what is f's output? 2. So f of g of 1 is equal to 2. This time we start on f. When f's input is 1, the output is 2. When g's input is 2, its output is 0. Starting with f, when f's input is -1, the output is -2. When the input's -2, f's output is -2. Start on the inside. When g's input is 2, its output is 0. So this becomes g of 0. When the input is 0, the output for g is 4. Okay. New tables now. This is kind of like number 12 in the composition packet. Again, these can be tough. Find the missing values in each table given h of x equals f of g of x. So this one especially, I need to write things out for. And the easiest table to fill out will be the h spot, just because it follows the formula directly. So it's the same thing. It's the same math that we were doing for 15 through 18. So I'm actually going to start with h. I want to find h of 0. So that should be f of g of 0. So whatever x you put into h, that's the x that you're starting out putting into g. Then work on the inside. What is g of 0? So when the input is 0, g's output is 5. When the input is 5 for f, the output is 2. Therefore, h of 0 is equal to 2. Okay. Now you might be able to guess, like you're just like, okay, this is probably 1 and this is probably 6. Like I made these tables up on my own, so they're not as creative. But if the numbers are more jumbled up, they're not just consecutive numbers, which it will be more like that for the quiz, you do need to be able to do the process. So even if you're saying, I'm guessing this is 1, I'm guessing this is 6, just looking at the numbers that we're working with, you need to know how to prove it. Okay, so with that said, these two are a little trickier because we're kind of working backwards. So let's start with f. We want to find f of 4. And according to our equation, that means that's f of g of something. But we don't know the something. That's kind of what we have to solve because we don't know what h of x corresponds to f of 4. It's not necessarily, well, it can't be h of 4. There is no h of 4. Okay, so let's go look at g's table. When g's output is 4, what is g's input? When its output is 4, its input is -1. So we want f of 4, which means we also really just want f of g of -1. And that tells us about h. That tells us h of -1. What is h of -1? We have that on our table. When the input's -1, the output's 1. Remember what f of g of -1 is? It's f of 4. So our answer is 1. Now, do you have to show all of these steps? No, but I think it's a good idea to write something down because it's easy to start looking at outputs instead of inputs or vice versa. Okay, what about g? So for g, I want to find g of 1. And how is this built into the function? Well, it's going to be f of g of 1 equals h of 1. We have h of 1. h of 1 is 3. Okay, so this one's a little different because we're saying, well, wait a minute. We're trying to find g of 1. Remember, g of 1 is an input. So let me bring this up here. What is the input for f that makes the output 3? So here's the output of 3, and the input is 6. What does that mean? It means that g of 1 has to be 6 to make this relationship work. Okay, so like I said, you could probably just guess, like, oh, this is going to be 1, 2, 3, 4, 5, 6, 1, 2, 3. That's because I was making this problem up on the fly, and I was just kind of doing something kind of quickly. But it's not about whether the numbers have a pattern or not. It's about following those same steps. These are the exact steps that I followed in the composite functions packet as well. Let me flip to that. This. So if you need to practice this again, I would erase those. And again, even though you kind of know what the answer should be, see if you can kind of prove it or explain it to somebody else. If you can explain math to somebody else, then that's like the best way to study, by the way. Explain to mom or dad or brother or sister or whoever. Okay, perform each combination and write the domain of the new function created. So remember, we will always write the domain. I'll prompt you to do it, but we will always write the domain when we're doing these problems that we're not plugging numbers into. So f plus g of x. Let's write down domain for each of these before we get started. So this is a square root function for f, so x plus 2 needs to be greater than or equal to 0. So x greater than or equal to negative 2. G is quadratic, so it's all real numbers. So where's their overlapping domain? If we're just working with the two functions, their overlapping domain is any x greater than or equal to negative 2, right? Because this one's all real numbers, and the only overlap would be f's domain. Okay, so knowing that, f plus g will just be the square root of x plus 2 plus x squared minus 11, comma, x greater than or equal to negative 2. That's it. There's nothing you can do to simplify that any further. You can't combine any like terms. F minus g is almost the same thing. Square root of x plus 2. We're subtracting all of g of x, so be careful with this. I say it's almost the same thing because there's a little bit of simplifying to do. Forgetting to distribute negatives is like the number one most common mistake that students make because we're not used to writing the parentheses. So if you get in the habit of writing parentheses every time, even though it's an extra step, it'll really help with that. The domain is still x greater than or equal to negative 2, so that if we were to go plugging numbers into this, we would get real numbers instead of imaginary. F times g, square root of x plus 2 times, you need parentheses here because you're multiplying by a binomial. You can't just write like a dot for times or something. And I'm not going to bother distributing the square root through because we're not doing anything with these functions, so there's no point to really working on them too much. Okay, and then for f divided by g, f is on top, g is on the bottom. Now this one's different because, and it'll be the quotient, the fraction problems where we might get some extra restrictions to pop up, because it's still true that x needs to remain greater than or equal to negative 2, but also x squared plus 11 can't equal 0 because now we've created this denominator. We don't want to divide by 0. So that would make x squared not equal to 11, which means x can't equal plus or minus the square root of 11, in addition to being greater than or equal to negative 2. Now, what is this as a decimal? You should be able to do this without a calculator, because think about this. 2 squared is 4. 3 squared is 9. 4 squared is 16. Where does 11 fall? Somewhere between 3 and 4. So square root of 11 is 3 point something. So when we say x value is greater than or equal to negative 2, the negative radical 11 is to the left of that. It's negative 3 point something, right? But we do need to consider the rest of the domain beyond that. So let me rewrite my function. So it's the square root of x plus 2 over x squared minus 11. And then what's my domain going to be? I'm going to say x, I'm just going to say it like this. X greater than or equal to negative 2, but x can't equal radical 11. I don't need the plus or minus. And I don't want you to put the plus or minus because that tells me you're not really thinking about what value this is. The negative square root of 11 is already out of this original inequality here. So anyway, so that would be your full credit. If this were on a quiz, this would be the full credit domain. Okay, now we have a new set of functions, so let's do the domain for these. So 3 minus x can't equal 0. That means that 3 can't equal x, or x can't equal 3. And then for the square root function, 2x has to stay greater than or equal to 0. So x has to be greater than or equal to 0. So combined, x needs to stay positive, but x can't equal 3. Or if you're using interval notation for any of these, then you would go like 0 to 3, 3 to infinity, including 0, but not including 3. All right, now, and I just showed their merged one, but now I'm looking at this. We're doing composition, so we actually don't care about the overlap. Let me get rid of that. What do we care about? We care about the inner function domain and then any new restrictions we get. So first know that composition means this. It's a good idea to sub in what g of x is. And then if you can train yourself to write down the domain restriction right there, this is the one that has to definitely make it to the end of our problem. Oops. How about I write the correct one though? Sorry. So g of x is square root of 2x. This is the domain restriction that has to make it to the end of our problem. And then when we plug that in to our function, 2 over 3 minus radical 2x, do we get any extra restrictions from this? Well, yes, because this denominator can't equal 0. So let's do some of that math. Let's see, that would be 3 can't equal square root of 2x. Square both sides. 9 can't equal 2x. Divide by 2. 9 over 2 can't equal x. Okay, so x needs to stay greater than or equal to 0, but can't be 9 over 2. Do I throw in x can't equal 3? No, because it's just inner function and final function. Okay, so f doesn't matter. If you plug 3 into this, you'll get 2 over 3 minus the square root of 6. That's fine. So let me write my final answer here. Actually, let me scooch this work around. It's the nice thing about computers. Okay, so this is the function. X should be greater than or equal to 0. X not equal to 9 over 2. Should I rationalize this denominator? You need to know how to do that if you're looking for multiple choice problems. But for now, I'm going to leave it because, like I said, I haven't been simplifying any of these. Not that there's anything to simplify for these two, but I haven't been distributing. I haven't been simplifying these much. I would just leave it like this. If you want to rationalize it, you'd be multiplying by 3 plus radical 2x, top and bottom. We'll get more into that down the line. Okay, what about the other way? G composed with f, you need to know that that's g of f of x. And that is g of 2 over 3 minus x. So here's where we make sure we say x can't equal 3. So now we care about f's domain. We don't care about g's domain, not yet anyway. G's function is the square root of 2 times x. So 2 times 2 over 3 minus x. Let's clean this up a little bit. That's 4 over 3 minus x. Okay, now we could square root this fraction a little bit more. It's like 2 over, square root of 4 is 2 over radical 3 minus x. The reason I would do that is because that'll make my domain piece a bit easier. We already said x can't equal 3, but now it's easier to see that you have a square root in a denominator. So this is the benefit of simplifying sometimes. So now I need to say, well, yeah, 3 minus x needs to stay greater than 0. 3 needs to stay greater than x, or x needs to stay less than 3, not including 3. So this is the function, 2 over radical 3 minus x less than 3. I would accept this answer as well, but you need to have x is less than 3 for your domain. So if you think you might not see that, if you see the square root of a fraction, it's worth at least looking at the fact that it's the square root of the top over the square root of the bottom. Okay, use these graphs. Now, fair warning, I have not checked this ahead of time to make sure it all fits, so you're kind of doing this with me. So I might make some corrections between my video and the end. We'll just see. So use the graphs of f and g to graph the following combinations on the domain 0 to 6. Okay, so first we're going to do f plus g. So I like making a chart because I've said this a lot. I really can't I'm not very good, I should say, at keeping all of these numbers in my head accurately and plotting them. So we're supposed to go from 0 to 6. So we're going to be plugging all of these x values in and seeing what we get. So when we plug in 0, we're adding the function values f plus g. So this is 3 plus 1, 2, 3, 4, plus negative 4, or just 3 minus 4. So the first point on the h of x graph is 0, negative 1. Okay, then go to 1. Okay, see? So here we go. So we're not going to plot the ones. We're only going to plot the nice points. I plotted these every 2 points. So let's not plot the odds because I don't want you to get an equation and figure out what all that is. Okay, so skip the 1. Do the 2. Okay, so when x is 2, we've got 2 plus or minus 2 plus negative 2, which is 0. So we're going to plot 2, 0. Go to 4. That's 1 minus 1, 2, 3, 4. So that's negative 3. So plot 4, negative 3. And our last one is 6. That's 0 minus 1, 2, 3, 4, 5, 6. So plot 6, 6, negative 6. I know these are connected with a line, with line segments, because both of these graphs are created with little line segments, so their combination would be as well. Okay, so I guess I'll throw an extra thing about these being just the evens. Okay, what about g composed with f? So this is one, again, we had this in our composite functions packet. G of f of x, and we're plotting 0, 2, 4, and 6. Okay, so let's make sure this works. G of f of 0. Okay, what does that equal? That's G of f of 0 is 3. Ooh, okay, so this one we're going to kind of estimate, okay? It's fine. It'll be fine because we can do slopes and stuff. Okay, so what's G of 3 going to be? So G of 3, where do we hit on this? Oh, this one's good. I can see that this would be a slope of negative 1 here, so I know that this is at negative 3. So I'm plotting 0, negative 3. Okay, G of f of 2. What does that become? So when the input's 2, where do we land on f? 2. And when the input's 2, where do we land on g? Negative 2. So we plot the point 2, negative 2. G of f of 4. I'm trying to be careful and make sure I'm on the right graph. When the input's 4 for f, the output is 1. When the input is 1 for g, we should hit at this integer point, negative 3. So we're at 4, negative 3. And g of f of 6. When the input 6, f is 0. What's g of 0? 1, 2, 3, 4, negative 4. So we're going to plot 6, -4, and we get this little guy. Okay, I also want to use this graph above for this graph. Okay, so we're going to double every y value and then shift to the right 4 units. So I'm going to need to zoom out so I can see this to write the points because I don't want to keep scrolling up and down. I want to write out my new points, and we're just on F. Okay, so nothing to do with G for this one. So instead of 0, 3, we're at 0, 6. Instead of 2, 2, we're at 2, 4. We're at 4, 2 instead of 4, 1. And this would still be 6, 0. And then everything's going to the right 4. Okay, so 0, 6 gets shifted to the right 4 units. 2, 4 goes to the right 4 units. 4, 2, right 4. And 6, 0 to the right 4. So we just have this little thing. This makes sense. Take a look at the original F graph. Had a slope of like -1/2. Now the slope is -1. We doubled that slope. It's still a line. It's been stretched vertically. All right, and now we're just looking at G's graph. So for G, every x value gets divided by 1/2. That's a horizontal dilation by a factor of 2. Every y value gets a negative, and then we're going up 5. So again, I'm going to zoom out so I can see the points. All right, so for G, let me erase there we go. For G on the original points here, so we have 0, 1, 2, 3. We have 0, -4. So that's still going to be 0, but now it's going to be +4. We have 2, -2. So this is going to be 4, +2. Excuse me. 4, -4 is going to become 8, +4. And I guess this one will be off the grid a little bit, but that's okay. We've got 6, -6. So this is going to become 12, 6. And then all of those will go up 5. So 0, 4. And then I'm going up 5 units. 4, 2. And then up 1, 2, 3, 4, 5. 8, 4. And then I'm going up 1, 2, 3, 4, 5. And this is the one that I will I still sketch it. It's a little bit off the graph. It's fine. 12 is like out here. 6. And then we're going up 5, which is just a little bit off the graph. And check the shape for G. The original shape was kind of like a check mark-ish. So this still is as well. Oop, this has been stretched horizontally. The points are farther apart in the horizontal direction, and it's been reflected and shifted up. Okay, what about the calculator part? There's not much to do on the calculator part. Our quiz will have just one calculator part question, and we're probably going to do this first this time. So a ship is traveling at 20 miles per hour parallel to a straight shoreline. The ship is 5 miles from shore. It passes a lighthouse at noon. The distance between the lighthouse and the ship is S of D, modeled by S of D. Square root of 25 minus D, where D is between 0 to 240. It's the distance in miles between the ship and its location at noon. Meaning the ship could be 0 miles from from its position at noon, or it could be 240 miles from its position at noon. The distance between the ship and its position at noon can be modeled by D of T. So the first one's the distance between the lighthouse and the ship, and now the ship and its position, where T is the time in hours since noon. Okay, so we have two distances. Distance between ship and lighthouse, and distance between, so like something like this, and then distance between, maybe at noon the ship was out here, and this is like the distance between the ship and where it was at noon. Okay, so find the composition S of D of T. Here's another reason I took this problem. It's kind of confusing and you don't even have to draw a picture. Like, it's kind of hard to picture all of this. But a lot of times we need to ignore a lot of the story of our AP problem and just get down to like, what do they want me to do? So they want me to find S of D of T. Without any context, if I can see these two equations, all that means is plugging D of T into S, right? And that means plugging 20t in for D in S's function. Square root of 25 minus, instead of D, minus 20t. And what would the domain be for that? Because I just wrote a new function. The domain, the only input variable is t. So the domain is what they gave me for t. This function is good for 12 hours. Interpret its meaning in context. So remember, what is S? S is the distance. Now here I go back to the problem. The distance between the lighthouse and the ship based on what's the input? Time since noon. Time in hours since, I guess I'll say 12 p.m. Or you could say noon. It's fine. So this is modeling the distance. Maybe I should say a model of the distance between the lighthouse and the ship based on the time in hours. Okay, now find the distance between the ship and the shoreline at 3:30 p.m. So when is 3:30 p.m.? How many hours past noon? That's t equals 3.5 hours. So we want to find S of 20 times 3.5. Or the way we wrote this in our notes was like S of D of 3.5. That's fine too. It does not matter. Here's where we hop over to our calculator and we type in our model for part A. So n for y equals, let's get all of this off of here. N for y equals, we put in the square root of 25 minus 20t, just put in x. Remember, the domain is important because it helps you set your window, 0 to 12. Zoom, it's option 0. I'm just going to press 0, but I'll show you where it is, just in case. Zoom fit is option 0. Oh, what? Okay, this is weird. And hold on, I'm just making sure I have the equation right. No, that's what it says. Okay, so yeah. Okay, so then when we get on here, we want to know when t is 3.5. Although something's wrong here. I wonder if I have a typo from this. Because let's see, 3.5. Here's what I would be doing. Yeah, there's no function for that. I think I'm missing a number here. I remember doing this problem and I feel like there's something that's supposed to be right here. All right, so I'm still going to show you the calculator stuff just to go through the steps of what you should do. And I will obviously have fixed this for your actual copy. So, all right, so what would we do if we had this function and we want to find the time at 3.5? We would say second trace value, type in 3.5, and press enter. Now, it'll give us a number once I have the correct equation in here. Okay, and then find the time at which the ship is 150 miles from shore. So this is saying when is S of D of T equal to 150? So I would be typing 150 on here. Okay, and it's not going to show up because, again, my function's messed up. I have some typo somewhere, like on the paper that I need to figure out. But if there were a line going through 140, let me make up a line. Yeah, this is going from, I bet it's not 25. It's probably 225. Let's see if I can make that adjustment. I think that's better. Okay, I think that's what my type. Oh, no, no, no. I think that's what my typo was. Maybe? Okay, I'll have to go back and look. That is a slightly better graph, but it's still not. There's still something wrong. Yeah, because the y minimax shouldn't be 1 to 15. Okay, anyway, um, what I was trying to say was if I had, so let me say I want to know when y equals 5, for example. So whatever this is going to be, when I put 150 into the other equation, I am looking for this point of intersection. So I do second, trace, intersect. And it just says first curve. It just means like if you have several graphs on here, it wants to know which two you want the intersection of. So just press enter. Second curve, press enter. Guess, press enter, and it'll tell you a point of intersection. Okay, this obviously is not the correct answer. I need to go back and find my find what the function should have been for this, and then I'll have it squared away for the key. All right, this is the only type of question we have for this quiz for the calculator. So you need to be able to write and interpret a composition function. You need to be able to plug in a time into the equation. We have several ways to do that on the calculator and get an answer. And then you need to be able to put a number into another y equals and find a point of intersection. All right, come to office hours if you have any questions.